we don't see anything in the packets to help us determine the bailiwick either. So we have to determine it ourselves from first principles. That's a relatively minor point. So we have to develop an algorithm that operates entirely passively. It's not allowed to make any inquiries of its own. It has to passively process each message and tell us for each record name in the response whether the IP address that sent us this response is really allowed to assert knowledge for that name. And this algorithm must provide a true or false value. It can't be a heuristic. We can tolerate a small number of false negatives if we have incomplete knowledge, but we cannot tolerate any false positives. That is the passive DNS bailiwick algorithm analyzes a DNS response and answers the question, for each record name, is the response IP address a name server for the zone that contains or can contain this name? For example, the root name servers can assert knowledge about any domain name and pass the bailiwick verification algorithm. And the GTLD servers, the .com and the .net servers, operated by VeriSign can insert knowledge about any domain name that ends in .com or .net, and in fact they did so for a short period in 2003. It's called VeriSign Site Finder. Very good. So here's how the algorithm works. First, we allocate a whole bunch of memory that will be used to cache the name server and address records after they've been verified by the algorithm. And we call this cache the bailiwick cache. And we initialize this cache using the entire root zone, which will give our algorithm knowledge of where the root and TLD name servers are, and thus it will know the bailiwicks of all the root and TLDs. Then, when we want to verify a given name against a given name server address, we find all the possible zones that the name could be located in, and whether the name server address in the response packet matches any of the addresses that are name servers for these possible zones. And finally, each time the algorithm successfully verifies an NS, A, or quad A record, that record is then inserted into the bailiwick cache. We're going to skip through the algorithm examples because they take a real long time to explain, and we want to get to the demos. Okay, what we call DNSDB is basically a database for permanently storing DNS records from a variety of sources along with a certain amount of metadata such as timestamps. Our primary data sources are passive DNS data, as well as a number of zone files that we have access to. Each record is serialized as an array of bytes, which we then store in an Apache Cassandra database. We don't have enough time to go over the exact serialization scheme, unfortunately, because it's really neat. We chose Apache Cassandra for a number of reasons. In particular, it's a distributed key value store, which means we can scale easily as the size of the database grows, and its data model provides a good fit for the type of data that we want to store. It's also extremely fast and can easily keep up with the amount of data that we need to process, primarily due to the fact that Cassandra always performs sequential writes, so we can make use of cheap, slow SATA storage. We then export the data stored in our DNS database via an HTTP API intended for bulk queries, as well as an interactive web search interface. And since we started loading data about a month ago, the size of our database has grown to about 500 gigs out of 27 terabytes total storage that we've deployed. We just bought some small little 2U boxes to test the thing out. DNSDB consists of several loosely coupled components. We have a number of data sources from which we receive new DNS data. And that's first most important source, of course, is the passive DNS. The first and most important source of DNS data comes from a program called InMessage DNS Cache, which processes the raw passive DNS data as it comes in from our sensors. And this is after it's passed the query response state inspection, and this program is now going to perform the passive bailiwick algorithm that we described earlier, and as that data comes in from the sensors. And the second source of data comes from the GTLDs that make daily zone file dumps available. So for instance, you can go to Verisign or Affilius and get access to daily dumps of their entire zones because of the contracts they have with ICANN that requires them to do so. And the third source of data comes from DNS zones, whose administrators allow us to perform zone transfers of their zones. This is currently our smallest source of data, and it's mostly just the ISC.org zone. And we're interested in adding more data via this method, since it's very cheap and easy to process in this manner. We then have data loaders that process the passive DNS data into batches of individual database rows and columns, and then connect to our Cassandra cluster in order to insert the processed data. So we have in-message DNS cache, which parses. I'm going to quickly go through the what it does, and then we'll get into the demo as soon as possible. It's a standalone program that reads the raw passive DNS data and parses each DNS message into a stream of individual, what's called resource record sets, and then we apply a series of filters before inserting each RR set into an in-memory cache. And these filters eliminate roughly 50% of the of data that we would otherwise have to store in the database. And RR sets that pass all the filters are then inserted into an in-memory cache, which we've tuned to store about 8 to 12 hours worth of data. And finally, the cache is expired in a strict first in, first out order, and these expired RR sets are sent over a socket, so the output can be stored for later processing and insertion into the DNS database. I think I covered this. So we sign up for the zone file programs, and we then we get the zone file dumps, but these are just the NS delegations. So in the .com zone, we see Google.com has these name servers, but that zone doesn't include all of the records that Google.com wants to serve, obviously, since the DNS is hierarchical and distributed. And then we can use passive DNS to fill in those gaps in the lower child levels of those zones. And this provides us with the TLD data provides us about 8 gigabytes of DNS data every day, and the passive DNS is probably a whole lot more than that. And we also operate a DNS server that slaves a few zones like ISC.org, and then when those zones get updated, we via AXFR or IXFR, zone transfer, and when those zones are updated, they get archived and processed and inserted into the database. This is a crazy, well, that's scaled poorly, but that's a crazy diagram of our architecture, and this will not be on the quiz. We apologize for that slide. Now we can start the demos. How much time do we have left? What time is it? It's 10:23. Thank you. I'm going to switch configurations real fast. Okay, this is the web interface. This is in pre-beta mode. Okay, let's see what we can find. Our domain name search allows us to do wildcard matches, which I don't think any of the publicly available passive DNS, searchable passive DNS databases allow you to do wildcard lookups. So this is a kind of a neat new feature that we've implemented. We're going to look at star.google.com, and we're going to only look at the records that are present in the top level com zone. So this means essentially name server delegation records and address records that are necessary for reaching the google.com name servers. So if we see anything out of the place in this particular domain, in this particular TLD, we know something is up. So here are the 4 matches that we get. Note that we have up to 4 timestamps associated with each match. This one has 4. These have 2 and 2 each. And we have a pair of first seen and last seen timestamps for data that was seen by passive DNS, and a separate set of timestamps for data that was seen in a zone file. So this indicates that this first match right here indicates that the google.com NS delegations were seen with these records from both the zone file and in passive DNS. And these down here say in zone file. So that means that without the other 2 timestamps, this indicates that these records were only seen in the .com zone. And if they weren't seen in passive DNS, that means that we might have a mismatch between the com servers and the google.com name servers. So we see these 3 records, A, B, and F.L.google.com, which are kind of interesting because these exist in the com zone, but not in the google.com zone. So let's click on this. And we get matches for 2 domains, 20comments.com and antifavlc.com. And supposedly Google is the name server for these names, or for these domain names. So let's click on this one, and we get a NS delegation for this domain. And supposedly, according to the .com zone file, this domain is hosted by Google, GTLD servers, and HRoot. For all the people that know about the DNS, this is an incredibly unlikely event to occur legitimately. So it looks like someone has invented a rather creative method of parking a name. And we can do some more clicking around, but I'm going to skip the rest of this example so we can get into some more interesting things. But basically there's a bunch of weird people out there that claim the root servers and the .com servers themselves are hosting their zones, which they don't. They only host the delegations to those zones. Okay. I am not a security researcher, but some of my best friends are. A good friend of mine recommended that this particular audience would be interested in all of the names that are hosted by SoftLayer. Apparently it's some sort of a colo hosting provider or something that for some reason people really dislike. So let's see what happens when we want to look up all the names that say SoftLayer's DNS servers serve. So we're going to do what's called an inverse query or an inverse search. The DNS originally had something called iQuery that worked very poorly, and apparently you have to build giant databases to support this. So we're going to put in a name, ns1.softlayer.com, and we want to know which domains they host. And here are 1,000 records. This has probably tripped over the maximum limit that the web interface has. So they must have a lot more than that. So we see all these different domains hosted by them. I was going to show you another SoftLayer example. I basically need a /16 that belongs to someone of interest. Unfortunately, I neglected to look up that information, so I'm going to use, should I use ISC as an example? Okay. Let's look up an IP or network match. I'm going to put in ISC's /16 and perform a search. Now this is really cool because it did it really fast. It eats /16s for breakfast. So here are a whole bunch of names that go into our ISC's namespace. There's a whole bunch of crap here. Someone is hosting a lot of domains for some reason. I can't imagine why that would occur. But here's basically all of the domains that are pointed into our address space. And this is interesting because the DNS is a forward delegation tree, so you don't really know who's pointing into your address space. So this is a very excellent monitoring